Hello, my name is Siddhant Bahadkar, and today I will be presenting my MSc Data Analytics project titled A Deep Learning Approach for American Sign Language Alphabet Recognition. This work was supervised by Vladimir Milosavljevic at the National College of Ireland. The focus of my project is to apply deep learning to accurately recognize American Sign Language alphabets in real time, helping to bridge the communication gap between the deaf or hard of hearing community and non-signers. Research objective and motivation. The main research question I explored is how can deep learning models be applied to accurately recognize American Sign Language alphabets in real time. The motivation comes from the need to improve inclusivity by providing an automated tool to interpret American Sign Language alphabets instantly, thus facilitating communication without requiring a human interpreter. This has practical applications in education, accessibility tools, and public service scenarios. Dataset details. As you can see in this visualization or diagram in this slide, shows how many folders are there actually, which contains the dataset in actual, which is used in my project. So the dataset consists of over 83,000 training images and 162 test images across 27 classes, including a nothing class. The images are in RGB format, originally sized at 200 by 200 pixels. Class labels are automatically generated from the folder names, and the mappings are saved in a class underscore indices.json file to ensure consistent label ordering during the predictions. Methodology overview. My approach used transfer learning with pre-trained ImageNet weights for several architectures like VGG16, ResNet 50, DenseNet 201, Inception v3, MobileNet v2, and a custom CNN. On top of each base model, I added custom classification head with dense layers, dropout for regularization, and softmax activation for multi-class output. The workflow involved, training, saving .h5 files for model weights and .pkl files for the model histories, evaluating, and finally performing real-time testing. So this diagram over here shows the system architecture from data input through to prediction. As you can see, there is an input first, then hand is detected inside the region of interest, then lots of pre-processing goes on. After that, class is predicted and output is displayed. For more details, you can refer to the report. During exploratory data analysis, I first looked at the class distribution. This bar plot shows that each class in the dataset has a roughly equal representation with about 3,100 images per class. Even though it may look like just balanced, but this balanced is nice because balanced dataset like this reduces the risk of bias towards any particular sign. Here you can see one example image from each class. So this visual check was important to verify image quality, variation, and that each class had the expected type of gesture. Training strategy. So for training, I applied image augmentations such as rotation, zoom, translations, shear, and horizontal flips. These augmentations simulate real-world variability and improve generalization. Base model layers were initially frozen and then gradually unfrozen in fine-tuning stages. Due to the GPU restraints on my RTX 3050, I used a batch size of 16. Callbacks included early stopping to prevent the overfitting and model checkpoint to save the best performing models. I typically fine tune for 15 epochs after the initial training. Training metrics. These are the training metrics for VGG16 because VGG16 consistently performed the best among all the other models. As seen in the training versus validation accuracy plot, accuracy improved from about approximately 30% initially to nearly 98%, while loss decreased steadily. The training was done in three phases. First, the initial training with frozen base layers. Second, fine tuning blocks 4 and block 5. And finally, fine tuning blocks 3, block 4, and block 5 for more optimal performance. These are the evaluation results of VG16. Though I did not include the confusion matrix visualization in the slides, but you can look for the visualization in my report for much more detailed. So as for the confusion matrix, it showed high precision across all the 27 classes. The overall test accuracy was 98.77%. The classification report includes or indicates most classes achieved perfect precision, recall, and F1 score with only slight drops in a few letters like G, H, M, and N. Real-time testing. So as for real-time testing, I used the fine-tuned VGG16 model. The webcam interface displayed a rectangular region of interest where the sign should be performed, as you can see in this visualization, which is just a sample of the how the window will look like. The user could press B to confirm the recognized sign, B to delete the last character, or Q to quit. This setup provided live feedback and could stream recognized characters, demonstrating practical usability. Configuration and environment. The entire project was developed on a laptop with an AMD Ryzen 5 CPU, RTX 3050 GPU, and 16 gigabytes of RAM. I used Python in a virtual environment with TensorFlow GPU version 2.10 and CUDA version 11.2 and CUDNN version 8.1.0. All the library versions were fixed using pipfreeze to ensure reproducibility. Trained models, histories, and class mappings were stored as .h5, .pkl, and .json files respectively. You can find the related data through my project in the code artifact provided. And if you want to look into much more detailed configuration and the versions of the libraries and every single library used, then you can just refer to my configuration manual. And as you can see, these are some of the key library versions which were used in the project too. So in conclusion, VGG16 offered the best trade-off between accuracy and real-time usability. And live classification was successfully demonstrated. In the future, this work can be extended to continuous gesture recognition, incorporate some temporal models like RNNs or transformers, and explore multimodal input using sensors such as IMUs. I thank you for your attention, for listening to all my presentation.